Welcome to Relaxing Wisdom. Settle in. Let your shoulders drop a little lower than they were a moment ago. There is nowhere you need to be tonight. Nothing you need to solve, no part of this story you need to hold on to. You can let it wash over you the way warm water moves over smooth stones, and if you drift off somewhere in the middle, that is exactly as it should be. The story will keep unfolding whether you are awake to hear it or not, and that, in a way, is the whole point of where we are going tonight. Because tonight we are going to travel further than almost any story can take you. Not across a country, not across an ocean, not even across the span of a single human lifetime or 100 lifetimes stacked end to end. We are going to travel 250 million years into the future to a version of this Earth so far beyond our own small moment that nothing you know, nothing you love, nothing anyone has ever built will leave the faintest trace upon it. And we are going to do it slowly, gently, like walking down a long staircase in the dark with a warm hand to guide you one step at a time, in no hurry at all. Here is the strange and quiet thing at the heart of it. The very gift that made us what we are, the gift that lifted our kind out of the shadows and let us inherit a whole world, is the same gift that in this far future could be the thing that ends us. Let me say that more plainly because it is worth sitting with. You are a warm-blooded creature. Right now, as you lie there breathing slow, your body is doing something quietly remarkable. It is holding itself at a steady inner warmth, somewhere around 37 degrees no matter what the room around you is doing. If the night grows cold, your body burns a little fuel and keeps you warm. You do not have to think about it. It simply happens, the way the tide simply happens. This is what scientists call endothermy, warm-bloodedness, the ability to make your own heat from the inside rather than borrowing it from the sun the way a lizard must, laid out on a rock in the morning, waiting to thaw. And this single trait, this inner furnace that never goes out, is one of the great quiet triumphs of life on this planet. It is the reason a mammal can hunt in the snow while the cold-blooded things lie still and slow. It is the reason a small, furred creature can be active at night, in the dark, in the cold, while the great reptiles wait for dawn. It is the reason, when the world fell into catastrophe 66 million years ago and the dinosaurs vanished from the earth in fire and dust and a long, darkened winter, that our distant ancestors, small, warm, hidden things, no bigger than a shrew, tucked into the roots and the burrows, survived. They survived the cold because they carried their warmth inside them. And when the smoke finally cleared and the world began again, it was these small, warm-blooded survivors who crept out into the empty light and, over the long, unhurried ages that followed, grew and spread and rose and filled the world. The whales in the deep ocean, the great herds on the open plains, the bats in the evening air, the bears, the wolves, the elephants, the mice, and you, lying here, breathing in the dark. All of it traces back to that small furred survivor and the warmth it carried inside its body when nearly everything else died. So warm blood is the inheritance. Warm blood is the crown. It is the very thing that let mammals take the earth. And here is the turn, here is the soft, strange irony that this whole long night is built around. 250 million years from now, that same warm blood, that same inner furnace that cannot be switched off, could be the precise reason mammals are written out of the story altogether. Because warm-bloodedness only works in one direction easily. It is wonderful at fighting the cold. You make heat, the world takes it away, and you stay comfortable. But when the world itself grows hotter than your own inner warmth, the whole arrangement begins to fail. A creature that runs hot on the inside has nowhere to send its heat when the outside is hotter still. The furnace that saved you in the cold becomes a furnace you cannot escape. And on the world we are traveling toward tonight, the outside grows very, very hot indeed, but I am getting ahead of myself, and there is no need to rush. We have all the time in the world. Truly, we have 250 million years of it. Let me bring you back to the present for a moment, to something you can feel in your own hands right now, tonight. Hold up your hand in the dark if you like, or simply picture it. Look at your fingernails. Think about how slowly they grow. You cut them and weeks pass, and they have crept forward only a little, a few millimeters, the smallest motion, so slow you can never catch it happening. You only ever see that it has happened. Now hold that pace in your mind, that patient, invisible creep. That is the speed at which the Atlantic Ocean is growing wider right now, tonight, as you lie here. The Atlantic is opening. Down the middle of it, on the floor of the sea, there is a long seam in the Earth's crust where new rock wells up from below, cools, and pushes the two sides apart. Europe and Africa drift slowly east. The Americas drift slowly west. And the ocean between them grows wider by about 2 to 4 centimeters every year, roughly the speed your fingernails grow. You would never feel it. No one alive has ever felt it. But over millions of years, that fingernail slow motion has done extraordinary things. It opened an entire ocean. It carried whole continents to the far sides of the world. And it has not stopped. The Atlantic is still widening tonight, patiently, silently, while the world sleeps. But here is the thing about a planet that does not change in size. If one ocean is growing wider, another ocean somewhere must be growing narrower. The Earth is not getting bigger, there is only so much room. And so as the Atlantic slowly opens, on the far side of the world, the Great Pacific Ocean, the largest ocean on Earth, vast enough to hold every continent inside it with room to spare, the Pacific is quietly dying. Around the rim of the Pacific runs a ring of deep trenches and grinding faults, a great circle of volcanoes and earthquakes that people call the Ring of Fire. And in those trenches, the floor of the Pacific is sliding down slowly beneath the continents that surround it, sinking back into the depths of the Earth, swallowed inch by inch, year by year. The Pacific is shrinking, not quickly. Nothing here is quick. But surely, over the long, unhurried ages, the largest ocean in the world is closing the way a great eye slowly closes in sleep. And that is the first great question of our long night, the question I want to hand to you now and let you carry with you, even into sleep. Which ocean dies? Does the Atlantic keep widening until something somewhere gives? Or does the Pacific finish its slow closing first? Because as we will see, the answer to that single question, which ocean lives and which ocean dies, decides almost everything about the world that comes after. It decides where all the land of the Earth will gather, and where the land gathers decides how hot it gets. That one slow choice written in stone and seawater shapes whether the future world is merely strange or whether it becomes a furnace too hot for warm-blooded life to bear. Hold that question gently. We will return to it. There is no need to chase the answer yet. Now, before we go any deeper, let me ask you something small and warm, because I'm genuinely curious. Wherever you are tonight, whatever country, whatever quiet room, whatever hour of the night has gathered around you, I would love to know. If you feel like it, sometime leave a word in the comments and tell me where in the world you are listening from. It is a strange and lovely thing to think of all these different places, all these different lives, all settling down to the same slow story under the same one sky. And if you are new here and you find that this slow kind of journey helps you find your way down into sleep, you might quietly subscribe so there will always be another long story waiting for you on another night. but there is no hurry in any of that either. You can do it half asleep tomorrow. For now, just rest. Because here is my promise to you for tonight. I am going to lead you slowly and carefully deep into one of the strangest and largest stories that science can tell. The story of the next supercontinent, the world that is coming long after we are gone, and the quiet, almost beautiful question of whether it will be too hot for creatures like us to ever live there again. We will go down into it the way you might walk down into an old, cool cave, one careful step at a time, the light dimming behind you, the air growing still. You do not have to keep up. You do not have to remember any of it. You only have to breathe and let the deep time carry you. So let us begin properly by stepping back, not forward but back, or just understand the great slow rhythm that this whole future is built upon, because what is coming has happened before, many times. This is the part that surprises people most, and it is the part that, once you understand it, makes everything else feel less like a catastrophe and more like a kind of breathing. The continents are not still. We feel them as still, and the ground beneath us is the very definition of solid, of unmoving, of permanent. When we want to say a thing will never change, we say it is set in stone. And yet stone is exactly the thing that moves the most over the long enough span of time. The continents drift, they always have. They ride atop the slow churning of the Earth's hot interior like rafts on a thick, syrup-slow sea, and over hundreds of millions of years they wander the whole globe. They crash together, they tear apart, they gather into great single masses, and then they break and scatter again. And then, after a long age of wandering, they gather once more. This is the supercontinent cycle. Some scientists call it the Wilson cycle, and it is one of the great heartbeats of our planet, a rhythm so slow that no creature has ever lived long enough to witness a single full beat of it, and yet so reliable that the Earth has been keeping this rhythm for billions of years. Let me walk you back through that rhythm gently, like turning the pages of a very old book, backwards into deeper and deeper time. The most recent supercontinent, the one whose name you may already know, was called Pangaea. The name means simply all Earth, all the land of the world fused into one. Pangaea existed from roughly 335 million years ago until about 175 million years ago. For all that vast stretch of time, there was effectively one great continent on Earth, a single enormous mass of land surrounded by one single world ocean. This was real. This is not a story or a guess. The fossils tell us, the rocks tell us. The same kinds of ancient creatures are found in lands that are now oceans apart, because once those lands were joined, and a creature could simply walk from what is now South America to what is now Africa without ever touching the sea. Pangaea was the rehearsal for everything we will talk about tonight, and we will come back to it, because what its harsh, dry, baking interior was like all those millions of years ago is a quiet warning of what the next supercontinent could become. But Pangaea was not the first. Before Pangaea fully assembled in the long ages leading up to it, the land had been gathering and shifting in other arrangements. Some scientists describe an earlier near-gathering called Pannotia, an older supercontinent that came together roughly 600 million years ago in a world so ancient there were no animals on land at all, no plants on land worth speaking of, only the sea full of strange early life and the bare stone continents empty under the sky. And before Pannotia, further back still, there was Rodinia. Rodinia gathered around 1 billion years ago, 1,000 million years before our own time, a number so large it stops meaning anything if you try to hold it all at once. When Rodinia existed, life on Earth was almost entirely microscopic. The whole grand pageant of animals had not yet begun. There were no fish, no insects, no trees, nothing that walked or crawled or flew. There was only the ancient ocean full of single living cells and the silent bare continents gathered together into one mass under a sky no eye had ever looked up into. And the earth held them like that, in that single embrace, before the slow rhythm pulled them apart again. And before Rodinia, deeper still into the dark of time, there was an even older gathering that geologists call Columbia, or sometimes Nuna, a supercontinent from perhaps 1.5 billion years ago, in a world we can barely imagine, where the very air itself had a different makeup, where the days were shorter because the Earth spun faster, and the young moon hung closer and larger in a strange sky. And before even that, at the very edge of what the rocks can still tell us, there was Kenor Land, one of the oldest gatherings of land we can still find faint traces of, from a time near the dawn of the continents themselves, when the Earth was young and hot, and the crust had only just begun to form the stable masses we would one day call continents at all. Do you feel the rhythm of it now? Kenorland, Columbia, Rodinia, Pannotia, Pangaea. Again and again, across thousands of millions of years, the land of the Earth has gathered itself into one, held that single embrace for a long age, and then slowly, slowly torn itself apart and scattered to the corners of the world, only to begin the long drift back together once more. Assembly, break up. Assembly again. Over and over, a breathing in and a breathing out, so slow that each single breath takes hundreds of millions of years. And here is the gentle truth that I find strangely comforting, lying here in the dark. We live inside a single breath of that rhythm. Right now, in our own brief moment, the continents are scattered. They are spread across the whole face of the Earth, the Americas on one side, Europe and Africa and Asia and Australia ranged across the other, with the great oceans filling the spaces between. This is a breathing out. This is the scattered phase. The last great gathering, Pangaea, broke apart and flung the continents to where we find them now, and they are still drifting, still riding their slow currents across the globe. But the rhythm does not stop. It has never stopped. And so the continents, scattered now, are already on the long, slow journey back toward one another. The breathing out will become a breathing in. Somewhere out ahead of us, hundreds of millions of years from now, the land of the Earth will gather itself into one great mass once more. There will be a new supercontinent, the next supercontinent. The Earth will draw a slow breath and pull all its land back into a single embrace, the way it has done 5 times or more before, and the way it will likely go on doing until the sun itself grows too fierce for any of it to matter. That is not a fear. That is not a doom. That is simply the planet breathing as it always has. There is something almost tender in it, the thought that long after every map we have ever drawn is meaningless, the Earth will go on keeping its ancient slow rhythm, gathering and scattering its continents in the dark, with no one left to watch. But, and here is where the story turns toward the strange thing at its heart, the thing that woke scientists up and sent them running to their supercomputers. Not every gathering is the same. Each supercontinent forms in its own place, under its own sky, in its own moment of the Earth's long life. And the place where the land gathers, it turns out, makes all the difference in the world. It is the difference between a supercontinent that is merely vast and strange and a supercontinent that becomes a trap, a planet-sized oven too hot for warm-blooded life to endure. Because the Earth itself is changing as the ages pass, the sun grows slowly brighter, the deep engines inside the planet shift their heat, and the land, when it gathers, can gather in a cool place or a fierce one near the gentle poles, or square upon the burning middle of the world. And whether the next supercontinent forms in mercy or in fire comes down in the end to that one question I handed you a little while ago, the question I asked you to carry into the dark. Which ocean dies? If the Atlantic wins its slow widening, if it keeps opening and opening until it pushes the Americas all the way around the back of the world to crash into the far side of Europe and Africa and Asia, then the land gathers one way, in one place. But if instead the Pacific wins its slow closing, if that great shrinking ocean finishes swallowing its own floor and draws the Americas and Asia together across the top of the world, then the land gathers somewhere else entirely, in a wholly different place, under a wholly different sky. Two oceans locked in a race so slow that the contest will not be decided for 200 million years or more, and two utterly different futures hanging upon the outcome. One world that gathers its land near the cool crown of the planet, and one world that gathers it square upon the equator, in the full and merciless face of the strengthening sun. These two possible futures even have names. Scientists have drawn the maps of both, run the numbers on both, given each its own quiet title. One is called Amasia, the other is called Pangaea Ultima, the last Pangaea, the final gathering, and the difference between them, the difference written entirely by which ocean lives and which one dies, is the difference between a strange new world and a world too hot to hold us. But we are not going to rush toward those two futures tonight. We are going to walk toward them slowly, the way we have walked toward everything so far, letting each piece settle before we reach for the next. There is no hurry. The supercontinents took billions of years to come and go. We can take our time. So let yourself rest here a moment on the edge of the question before we go further down. Let it be enough for now simply to know this much: that the ground beneath you is not still, that it drifts fingernail slow across the face of the earth, that it has gathered into one great mass 5 times and more across the deep ages, and scattered 5 times and more, breathing in and out across the eons, that right now, in our own small moment, the Atlantic is widening and the Pacific is dying, and the land is already drifting with infinite patience toward its next great gathering, and that somewhere out ahead of us, hundreds of millions of years beyond any human concern, a new and final supercontinent is waiting to be born, and that the place it chooses to be born could decide whether the warm-blooded creatures of the earth, the long inheritors of that small furred survivor from the age of the dinosaurs, can go on living upon the world at all. That is where we are going tonight, down into that question, slowly, gently, all the way to the bottom. And the deeper we go, the stranger and more beautiful it becomes, because as we will see, it is not only the place the land gathers that turns the world into a furnace. The trap, when it closes from more than one direction at once. There is the place the land sits, yes. But there is also a sun that is slowly, measurably growing brighter overhead. And there is a deep fire within the earth itself, stirred to life by the gathering of the continents, that breathes its own heat into the sky. 3 slow forces, 3 patient hands, all reaching for the same far-off moment from 3 different directions. And we will trace each one of them in turn, with all the time in the world. But the very first of those 3 hands, the one that decides everything else, is still that single quiet question, drifting now beneath the floor of 2 oceans on opposite sides of the sleeping earth. Which one closes, which one opens? Where the land will choose to gather when at last it gathers again. Let that question drift with you now down towards sleep, unanswered and in no hurry to be answered. We will follow it into the deep tomorrow, or in the next breath of this long night, whichever finds you first. For now, there is only the slow turning of the earth beneath you, the continents drifting their fingernails' slow drift, the oceans opening and closing in the dark, and you, here, safe, in this one small, warm moment that the whole vast story has somehow made room for. Welcome to Relaxing Wisdom. And if you are new here, drifting in for the first time tonight, you might let the channel know where in the world you are listening from, somewhere down in the quiet below this story. And if these slow journeys help you find your way to rest, you might gently subscribe so the next one finds you when you need it. There is no hurry in any of this. There never is in deep time. Now, let us begin where the irony begins. 66 million years ago, something ended the long reign of the dinosaurs. The end Cretaceous extinction it is called, and in its aftermath, the great reptiles that had ruled the land for 150 million years were simply gone, and the world they left behind was open, empty, waiting. Into that emptiness crept a small, soft, unremarkable kind of creature, warm-blooded, furred, able to hold its own heat inside its own body, no matter what the air outside was doing. And that one quiet gift, that warm blood, that endothermy, was the thing that let those small creatures spread out into the empty world and inherit it. Our ancestors. The first mammals to truly rise. Think of what a gift it was. To carry your own warmth with you. To wake in the cold dark of a winter dawn and already be warm, already be ready, while the cold-blooded things around you lay stiff and slow, waiting for the sun to lend them the heat they could not make themselves. The mammals did not have to wait. They made their own fire and carried it inside. And on the strength of that inner fire, across 66 million years, they became everything. The whale and the bat, the wolf and the mouse, and eventually the listener lying here in the dark, holding their own small warmth inside their own chest, breathing slow. But here is the strange and beautiful turn of it. That same warm blood, that same inner fire that let mammals inherit the earth, is the exact trait that 250 million years from now could write them out of the story entirely. The gift becomes the trap. The thing that let us in becomes the thing that locks us out. And it does so not through any disaster we would recognize, not an asteroid falling from the sky, not a dying sun swelling to swallow the world. Something far slower and far stranger. Our own planet's quiet tectonic breathing. The slow drift of the continents themselves. Because the continents are moving, even now, even tonight, beneath everything that has ever been built or buried or loved, the ground itself is drifting, and it is drifting at the speed your own fingernails grow. 2 centimeters a year, perhaps 4. Slower than thought, slower than memory, but never, ever stopping. The Atlantic Ocean, that vast grey water between the old world and the new, is widening right now, pushing the Americas a little further from Africa and Europe with every passing year by exactly that much, the width of a growing fingernail. And on the far side of the world, the Pacific, the great ocean, the largest single feature on the face of the planet, is quietly closing, quietly dying, its edges ringed with the deep trenches where its floor slides down and under and back into the earth, swallowed, recycled, gone. So one ocean opens and one ocean closes, and the land between them drifts its fingernail slow drift, and somewhere very far ahead, the land will gather again. It has done this before. That is the thing to hold on to here at the edge of sleep. This is not a one-time accident. This is a rhythm. The supercontinent cycle, the geologists call it, or sometimes the Wilson cycle, and it is as established and as patient as anything in all of science. Across hundreds of millions of years, again and again, the continents have wandered apart across the face of the world, lonely and scattered, and then, slowly, slowly drifted back together into a single vast landmass, only to break apart once more. Assembly and rifting, gathering and scattering, the deep, slow breathing of the Earth. The last great in-breath gave us Pangaea, the supercontinent that existed from roughly 335 million years ago to 175 million years ago, a single fused landmass you could have walked across from pole to pole before it cracked apart and drifted into all the continents we know today. But Pangaea was only the most recent breath. Before it, there was Pannotia. And before that, going back more than 1 billion years, there was Rodinia, vast and ancient and almost unimaginably old. And further still, into the deep dark of the planet's youth, Columbia, sometimes called Nuna. And older even than that, at the very edge of what the rocks can still remember, Kenorland. Names like the names of forgotten gods. Each one a single slow breath of the earth, each one assembled over hundreds of millions of years, held for a while and then let go. And we, all of us, every human who has ever lived, every mammal that ever drew breath, the dinosaurs and the trilobites and the first green things that crawled up onto the land, all of us have lived our entire histories inside the long, slow exhale that followed Pangaea. We have never once seen the in-breath. We have only ever known the scattering. But the in-breath is coming, the continents are wandering home, and when they gather again into the next supercontinent, the place where they choose to gather will decide the fate of everything that lives on them. Because geography, as we will come to see across this long night, is destiny. And the single quiet question that decides that destiny, the question hiding right now beneath the floors of two oceans on opposite sides of the sleeping world, is this: which ocean dies? If the Atlantic stops its widening and turns and begins instead to close, the Americas will come swinging slowly back the way they came, folding once more into Africa and Eurasia, gathering near the warm middle of the world, near the equator, into the supercontinent the scientists have named Pangaea Ultima. And if instead the Pacific is the one that finishes its dying, then the gathering happens somewhere else entirely, far to the north, and a different world is born with a different fate. One choice, made by the patient drift of the seafloor across 250 million years, one ocean closing while the other opens, and the temperature of the entire future world hangs upon which one it is. That is the master question of this whole long story: which ocean dies and what that single choice does to the heat. Hold it loosely now, let it drift down with you into the dark, unanswered, in no hurry at all. The seafloors are moving even as you breathe, settling the matter so slowly that no living thing will ever feel the moment it is decided. Let the wisdom settle soft, the rest will come on its own. And so we begin with the two futures, two worlds, that the same set of wandering continents might become, depending on that single patient answer from the seafloor. It is worth dwelling here, in the space between them, because this is where the story truly opens. Not in some abstract tectonic diagram, not in the spiraling animation of land masses converging like puzzle pieces drawn together by a magnet, but in the physical reality of what it means for land to gather in one place versus another. The where of it. Because the where, as we shall slowly understand, is almost everything. Think for a moment about standing outside on a summer afternoon, two different afternoons in two very different places. In the first, you are on a coast somewhere, close enough to the sea that you can feel it, that there is salt in the air and a breeze coming off the water, cool and damp against your skin, the ocean breathing out its moderation onto you, borrowing the excess heat from your body and carrying it away. The temperature is high, perhaps, but manageable. The sea is doing its quiet work all around you, holding the heat down, smoothing the edges off the day. And in the second, you are deep in a continent's interior, far from any ocean, in a place like the heart of Central Asia or the red centre of Australia, where the nearest coastline might be 1,000 kilometers in any direction, and the ocean's reach does not extend. There the afternoon is a different kind of creature entirely. Hotter, more absolute, less forgiving. The same latitude, the same angle of sunlight, the same seasons, and yet a world apart in what the heat does to a body standing in it. That difference, the gap between the coast and the interior, has a name. Scientists call it continentality, and it is one of the foundational principles that will determine whether the next supercontinent becomes merely warm, or whether it becomes something close to uninhabitable for most of the complex life that has inherited this planet. We will return to continentality to the full weight of what it means when you take it to its theoretical extreme a little later in this long night. For now, hold it simply as a felt thing. The difference between that sea-cooled afternoon and that dry, absolute interior afternoon. That difference taken to its largest possible expression. First, the two futures. The scenario that the scientists at the University of Bristol chose for their 2023 modelling study, the one that would go on to produce the numbers that stopped a great many people very suddenly when they read them, is called Pangaea Ultima. You will also sometimes see it written as Pangaea Proxima, both names pointing at the same idea, which is the next Pangaea, the last Pangaea, the one that closes the circle on the one before it. The logic of its formation runs as follows. The Atlantic Ocean is currently widening. You know this already from the first part of this night's journey, the spreading ridge running down the middle of that ocean, new seafloor being born there continuously and pushing the old seafloor outward toward the continental margins, adding a few centimeters of ocean floor every year. But seafloor does not accumulate forever. Eventually it reaches the edges of the ocean basin and it encounters the edge of the continent. And when dense ocean floor meets the lighter rock of a continent, the denser material goes under, it subducts. It dives back into the mantle from which it originally came. And this is happening all around the world right now at the places we call subduction zones. The question for the Atlantic is whether it will eventually develop robust subduction zones along its margins, the margins that line the Americas on one side and Africa and Europe on the other. And if it does, whether those subduction zones will consume the ocean floor faster than the ridge can produce new floor, causing the ocean to eventually narrow and close. If that happens, the Americas will begin to move back toward the east. Not quickly, not in any time frame that would register in a human life or 100 human lives or 10,000 human lives, but over tens of millions of years, and then over 100 million years, and then approaching 250 million years from now, the Americas sliding slowly back the way they came, and the Atlantic narrowing behind them, and the ocean that has been widening since the Jurassic finally reversing its long outward breath and drawing back in. And as it closes, the continents converge. North America drifts toward Europe. South America folds back toward Africa. The islands and microcontinents that dot the ocean between them are pushed aside or subducted or scraped up onto the margins of the gathering land. And eventually, a geological eternity from now, they meet. The Atlantic closes, the land masses suture together. And what emerges from that long, slow collision is a supercontinent centered somewhere in the tropics, somewhere near the equatorial belt of the planet, a vast gathering of land pulled together in precisely the part of the world where the sun delivers the most energy per square meter of surface. This is Pangaea Ultima, a word that carries the weight of finality in it, as names sometimes do. The other scenario works from the opposite direction entirely. The Pacific Ocean is already dying. This is not a metaphor, and it is not a projection. It is a present tense geological reality. The Pacific is ringed on almost all sides by subduction zones, the places where the Pacific seafloor is already diving under the surrounding continents and island arcs, being swallowed back into the mantle. The Ring of Fire, the great arc of volcanic mountains and earthquake zones that encircles the Pacific Basin from New Zealand up through Japan and across to Alaska and down through the Americas, all of that volcanic and seismic activity is the surface expression of the Pacific seafloor being consumed. The Pacific is getting smaller year by year, centimeter by centimeter, while the Atlantic grows. The two great oceans breathing in opposite rhythms, one expanding while the other contracts. If the Pacific is the ocean that closes fully, then the Americas do not swing back east. Instead, they drift west, across what remains of the Pacific, and eventually they converge, not with Africa and Europe, but with Asia. The continents gather not at the equator, but at high latitude, perhaps near or over the North Pole. And the supercontinent that results from this polar convergence has been given the name Amasia. The research that developed this scenario in its 2022 form came primarily from a team at Curtin University, led by a scientist named Chuan Huang, and it presents a world that is in some ways the geographical inverse of Pangaea Ultima. Instead of a massive tropical and subtropical landmass baking in the belt of maximum solar energy, you get an enormous polar or subpolar landmass gathered in the latitudes where the angle of sunlight is lowest, where winter brings months of near darkness, where cold is the dominant climatic register across much of the land. And here is where the where begins to matter enormously, because Amasia and Pangaea Ultima are not simply two different maps, they are two different fates. They are, in a very real sense, two different worlds. And the path to each of them is driven by the same engine, the same deep mechanism hidden in the body of this planet, which has been running for billions of years, and which will continue to run long after the last mammal has either found shelter at the margins of an unrecognizable world or disappeared entirely from the living record. That engine is plate tectonics. And before we can understand what comes next, we need to feel how it works, in the way that a sleeper might feel the slow turning of the earth beneath them, not as a fact to remember, but as a process to inhabit. The lithosphere, the outer shell of the earth, the hard rocky layer that includes both the crust and the upper part of the mantle beneath it, is broken into pieces. You can think of it the way you might think of the cracked shell of a hard-boiled egg if the egg were a sphere roughly 12,000 kilometers across, and the cracks in the shell were hundreds of kilometers deep at their thickest, and if the pieces of shell were moving slowly and continuously, driven by forces operating in the hot, semi-solid rock beneath. Those pieces are the tectonic plates, about a dozen major ones and a scattering of smaller ones, each carrying some combination of continental crust and oceanic crust on its back, each moving at rates that are slow beyond easy imagining, centimeters per year, in most cases the rates of fingernail growth and hair growth and the slow accumulation of geological sediment. What makes them move? There are two primary forces and they work together. The first is something called slab pull. When an oceanic plate reaches a subduction zone, it bends and dives into the mantle, and as it does, the cold, dense material of the old seafloor is heavier than the surrounding hot mantle rock, and it sinks. It pulls the rest of the plate behind it, the way a tablecloth pulled off the edge of a table would pull the rest of the cloth with it, if the tablecloth were thousands of kilometers long and moved at the pace of geological time. This slab pull is considered the dominant driver of plate motion. The cold old slabs diving into the mantle are, in a sense, pulling the whole surface of the planet slowly toward the subduction zones, dragging continents with them. The second force is called ridge push. At the mid-ocean ridges, where hot mantle material wells up and creates new seafloor, the young ocean floor is warmer and therefore slightly elevated. You can think of the ridge as a long underwater mountain range built from the heat below. As the new seafloor spreads away from the ridge and cools, it also subsides, sinking lower. That gentle slope from the high, warm ridge down to the cooler, lower flanks of the ocean basin creates a gravitational push outward from the ridge, a nudge quieter than the slab pull but present, contributing to the motion. And what powers all of this ultimately is heat. The internal heat of the Earth itself, accumulated from two sources that have been present since the planet formed. The first is primordial heat, the heat generated during the violent formation of the Earth 4.5 billion years ago, when uncountable collisions of rock and dust and larger planetesimals generated enormous energy, and much of that energy was buried deep inside the young planet. Some of that original heat is still there, still slowly leaking out through the mantle and the crust, still contributing to the churning convection in the mantle that drives plate motion. The second source is radioactive decay. Inside the Earth, there are long-lived radioactive isotopes, uranium, thorium, potassium, that are decaying continuously, releasing energy as they do, and that energy becomes heat. These two sources, primordial and radiogenic, have been warming the planet's interior since before life existed, and they are, in the deepest sense, what makes the surface move. You could think of it this way. The Earth is a very slowly cooling body, releasing its internal heat through the convection of the mantle, and that convection is what fractures the outer shell into plates and drives those plates across the surface in the patterns we observe as plate tectonics. The whole vast drama of continents gathering and rifting apart, of oceans opening and closing, of mountain ranges rising and erosion slowly wearing them down. All of it is the surface expression of a planet leaking its internal warmth. And the planet is very slowly, very gradually getting cooler. The radioactive isotopes are decaying, and over billions of years their contribution to the internal heat budget decreases. The primordial heat is being lost, dissipating over geological time. And as Earth's interior cools, the driving engine of plate tectonics will eventually slow and perhaps stop entirely in the far future, though not within the time scale we are visiting tonight. For now, and for the next few 100 million years at least, the engine runs, the plates move, the oceans open and close, and the question of which ocean closes first, which one is swallowed by its surrounding subduction zones before the other, is being answered right now in the dark of the seafloor, in the slow creep of cold, dense rock back into the mantle at 1,000 separate points around the ring of fire. Let us stay with the ring of fire for a moment, because it is worth understanding what it looks like, what it represents, and what it is quietly doing. If you were to draw the Pacific Ocean on a map and then draw a line around its edges, following the chains of volcanic mountains and island arcs and earthquake zones that form its border, you would trace a rough oval encircling most of that ocean. Japan, the Philippine Islands, New Zealand, the volcanic arc of the Western Pacific Island chains, Alaska, with its own arc of volcanic islands reaching out into the Bering Sea, the Cascade Mountains of the American Northwest, the volcanoes of Central America, the Andes rising along the entire length of South America's western coast. All of these are the surface evidence of subduction. All of them are places where oceanic plates are diving under other plates, and where the descending rock, as it goes deeper and the heat and pressure mount, releases water and volatiles that lower the melting point of the rock above it and generate magma, which rises and erupts at the surface as volcanoes. The Ring of Fire is the Pacific giving itself back to the mantle, piece by piece, kilometer by kilometer, in geologically slow motion. And as the Pacific is consumed at its edges, it shrinks. The Atlantic, meanwhile, has no comparable system of subduction zones along its margins. At least not yet, not in a form robust enough to outpace the ridge's production of new floor. The eastern seaboard of North America and the western coast of Africa are what geologists call passive margins, tectonically quiet. The continents there simply resting at the edge of the widening ocean. So the Pacific dies while the Atlantic grows, And the question of whether the Atlantic will eventually reverse and begin to close, developing its own subduction zones and consuming its own floor, or whether the Pacific will finish dying first and pull the Americas west. That is the open question at the heart of the two future scenarios. Scientists work with both possibilities not because they cannot do the maths, but because the mathematics of future plate motion become genuinely uncertain over the time frames we are discussing. Tens of millions of years out, tectonic forecasting is still relatively constrained by what we can observe today. But as you push toward 250 million years, the uncertainties compound. Small differences in initial conditions in where new subduction zones initiate and how fast they develop can lead to very different long-term outcomes. The two named scenarios, Pangaea Ultima and Amasia, are not competing predictions in the sense that one will be proved right and one wrong. They are genuine scientific possibilities, each grounded in plausible extrapolations from the current state of the planet. But what the 2023 Bristol study chose to model was Pangaea Ultima, the equatorial gathering. And the reason that choice matters, the reason the equatorial location is so consequential for what comes next, is inseparable from the principle of continentality and from something that Pangaea, the most recent supercontinent, showed us very clearly in the geological record. Pangaea was real. It is not a future projection or a theoretical construct. It was the most recent in a long series of supercontinents that Earth has assembled and then broken apart over the course of its long history, and it is the one for which we have the richest and most detailed evidence because it is the most recent and the record of it has not yet been completely erased by the passage of time. Pangaea began forming roughly 335 million years ago as the preceding fragments of older supercontinents converged in the Carboniferous and Permian periods. It was fully assembled somewhere around 300 million years ago, and it persisted for over 100 million years before it began to break apart in the early Jurassic about 200 million years ago. Its final fragments, the last pieces of the old unified landmass, separated somewhere in the region of 175 million years ago, and since then those fragments have been drifting to the positions we now call the modern continents. During the time that Pangaea existed, it created a climate unlike anything the Earth experiences today, and that climate is one of the most important pieces of evidence we have for understanding what the next supercontinent might do to life. The fundamental fact about Pangaea's climate is that it was extreme, not uniformly hot, not uniformly cold, extreme. The vast interior of the single landmass, the deep heart of it, far from any ocean shore, experienced temperature swings that no coastal or island location would ever see. Summer temperatures in the interior reached levels that would be lethal for most modern mammals. Winter temperatures in the same places dropped to levels that would freeze unprotected ground. The range between summer and winter in the deep interior of Pangaea was in places staggering. This is the geological record of continentality operating at continental scale, in a world where the continental interior was so vast and the ocean so far away from its heart that the moderating influence of water effectively could not reach. There was also a climate system that developed over Pangaea that geologists call the mega-monsoon. You are perhaps familiar with modern monsoons, the seasonal reversal of winds that brings the wet season to South Asia and parts of Africa and Australia, driven by the differential heating and cooling of land and ocean. During the northern summer, the Asian continent heats rapidly, while the Indian Ocean stays relatively cool, and this temperature difference drives a flow of moist ocean air northward and inland, bringing the monsoon rains. During winter, the pattern reverses, the continent cools faster than the ocean, and the winds turn, bringing dry conditions. This is the monsoon as we know it, driven by the size of the Asian continental landmass and its contrast with the surrounding ocean. Pangaea had a monsoon system of a quite different scale. With all the land gathered into one mass and all the ocean distributed on the outside of it, the seasonal temperature contrast between the supercontinent and the surrounding ocean was extreme beyond modern comparison. The mega-monsoon that resulted was correspondingly vast, a seasonal wind reversal operating at a global scale, bringing seasonal rainfall to some coastal and near-coastal parts of the supercontinent, but in the deep interior, doing very little. Because the interior was so far from the ocean, the moisture from the ocean's surface had evaporated and rained out long before the winds could carry it that far inland. The heart of Pangaea was arid, dry, and dramatic in its temperature range. The geological record in rocks from that period shows vast expanses of desert sediments, ancient dunes, salt flats, and the kinds of deposits that only accumulate in conditions of extreme aridity and heat. Pangaea's interior was something like the largest desert the Earth has ever known, enclosed by coastal zones where rainfall varied widely by season and latitude. This is the proof of concept. This is Earth having already done something close to what we are projecting for the future, having already assembled its land and then experienced the climate consequences of that assembly, having already demonstrated in rock and sediment and ancient soil horizons what continentality looks like when it is taken to its greatest expression. The geological record of Pangaea is not just history, it is a warning, written in stone 300 million years in the making and already there to be read by anyone who knows how to look. And now we come to continentality itself, to the principle that the existence of Pangaea demonstrates so powerfully, and we need to feel its workings before we can understand why a future supercontinent gathered at the equator might be so different, so much more dangerous than a cooler version of the same idea assembled somewhere near the poles. Water is unusual. Among the common substances of the Earth's surface, it is unusual in the amount of heat it can absorb before its temperature rises. This property is called specific heat capacity, and water's is exceptionally high. What this means in practical terms is that you can pour a great deal of energy into a body of water, sunlight, warming air, and the temperature of that water rises only slowly. Equally, when you remove energy from water and when the nights get long and the air cools, the water gives up that stored heat slowly. It does not cool quickly. The ocean is a vast heat reservoir, soaking up warmth in summer and releasing it gradually through autumn and winter, damping the swings. If you live near the ocean is your climate's thermostat. Land does not behave this way. Rock and soil have a much lower heat capacity than water. They heat quickly under sunlight and cool quickly when the sunlight goes. A rock in the desert can be too hot to touch in the afternoon and cold in the night. A vast continental interior exposed to the full energy of the sun through a long summer with no ocean nearby to moderate the temperature will reach extremes that a coastal location at the same latitude never would. Today, this principle operates at the scales our world allows. The interior of Central Asia, which is perhaps the most extreme modern example of continentality, experiences winter temperatures that can drop below -40 degrees Celsius and summer temperatures that can climb above 40 degrees Celsius in the same location, a range of 80 degrees or more between the cold extreme and the hot extreme. This is a place like Ulaanbaatar in Mongolia or parts of Siberia, or the high deserts of Central Asia, where the ocean's reach simply does not extend, where the air that arrives has already shed its moisture on mountains and ranges far to the west or east, where the seasons are raw and absolute. Central Australia, though at lower latitude, has its own version of this. The vast red interior swings between extreme heat in summer and cold desert nights, and its aridity is directly related to its distance from the moderating ocean. On the modern Earth, these extremes are limited by the size of the existing continents. Even the largest single landmass today, Eurasia, is surrounded by ocean on all sides, and while its interior is extreme by modern standards, it is bounded. The ocean is always somewhere not impossibly far away. Weather systems carry moisture inland to some degree. The extremes are real, but they are moderated by the geometry of a world where land is distributed across the surface in many separate pieces with ocean between them. Now imagine all of that land gathered into one. A single supercontinent. Not Eurasia, which is already a large joined landmass, but something far larger. All of Eurasia, plus the Americas, plus Africa, plus Australia, plus Antarctica, all of them sutured together into one unbroken expanse of rock and soil. The interior of such a landmass would be thousands of kilometers from the nearest ocean in every direction. Not the 1,500 or 2,000 kilometers that the deep interior of modern Eurasia sometimes manages, but thousands, 3,000 kilometers, 4,000, perhaps more, depending on the geometry of the final assembly. And in those deep interior regions, the ocean's thermostat would be entirely absent. The heat that accumulated in the rock and soil through the long hot days would have nowhere to go. The moisture that would normally come from ocean evaporation and be carried inland by winds would rain out long before reaching the interior. The air arriving at the heart of such a continent would be dry, having crossed thousands of kilometers of land already, and it would be hot, and the daily and seasonal temperature swings would be enormous. This is continentality made absolute. This is the principle that the existence of Pangaea already demonstrated, now taken forward in time and combined with additional factors that were not present when Pangaea existed, factors that will make the future version significantly worse. We will come to those additional factors, and to the scientists who measured them, in the next movement of this long night. But for now, let the scale of continentality settle into your understanding. An ocean is a buffer. Take away the ocean and you take away the buffer. Gather all the land into one place and you have removed the buffer completely for any creature standing in the interior. And then consider where Pangaea Ultima gathers that land. Not at the poles, where the angle of sunlight is low and cold moderates heat. Not at high latitudes, where the long polar winter provides at least a seasonal respite. But at the equator, and in the tropics, and in the subtropics. In precisely the band of the planet where the sun hits most directly, where solar energy per square meter of surface is at its maximum, where the heat is already greatest under our current geography. Pangaea Ultima, in the model that the Bristol team chose to run forward, places the bulk of its enormous single landmass in the zone where the Earth is already warmest. And that is before anything else changes. That is just the geography, just the shape, just the location. That is continentality plus equatorial positioning, two of the three forces that the 2023 study would identify as stacking together to produce the temperatures that would follow. Two of the three directions from which, as Alexander Farnsworth and his colleagues would eventually conclude, the trap closes. Amasia offers a different geometry. Gathered at high latitude, perhaps centered near or over the pole, it would place much of its interior in the zone of low solar angles and long polar winters. The continentality would still operate. The interior would still be far from the ocean, still extreme in its seasonal swings, but the extremes would be cold extremes more than hot ones. A polar supercontinent would be bitterly cold in its interior rather than lethally hot, and while extreme cold is also a challenge to life, it is a different kind of challenge, and one that mammals, with their ability to generate internal heat and to grow insulating fur, might be better placed to endure than the alternative. The temperature destiny of the next supercontinent, then, is not written yet. It hangs on which ocean closes, the equatorial trap of Pangaea Ultima versus the polar deep freeze of Amasia. And the 2023 study, with its supercomputer and its climate model and its stacked drivers, chose to run the numbers on the equatorial version. The the version that gathers the land where the sun is strongest, and then adds to that geography two further forces that Pangaea itself did not have to contend with in the same measure. The sun was dimmer when Pangaea existed, and the supercontinent that forms 250 million years from now will form around a sun that is measurably, significantly brighter than the one that shines today. This is the third element, the third direction from which the trap closes, and it is one that no tectonic repositioning and no geological process can alter. It is simply physics, and it is already in motion, and it changes everything. But that is for the next movement of this long, slow descent. For now, let the two futures rest in your mind alongside each other, the equatorial gathering and the polar one, the Atlantic closing and the Pacific closing, Pangaea Ultima and Amasia. And let the principle of continentality settle into your body the way a night chill settles in from the edges of an open window, quietly and without announcement. The earth breathes, the continents drift, the oceans open and close in rhythms that outlast any creature that has ever lived upon this surface. And deep inside the planet, the ancient heat is leaking out through convection and volcanism and the slow creep of plates, driving the whole long drama at a pace so unhurried that it can only be perceived across the span of deep time, across millions of years, laid down in rock and reed, back by patient science. The ring of fire continues its slow work in the night. The Pacific floor is diving back into the mantle, kilometre by silent kilometre, returning to the deep place from which it came. The Atlantic is breathing out, its ridge producing new floor with every year that passes. And the answer to the question of which ocean closes is accumulating somewhere in the dark geometries of the seafloor, in the balance between production and consumption, in the slow initiation of new subduction zones along old passive margins, in processes so gradual they could be said to be patient in the way that only geological processes are patient. You do not need to hold the answer tonight. You do not need to carry it forward into whatever dream is beginning at the edges of your awareness. The continents will not hurry for you, and they will not hurry without you, and the question will resolve itself over time scales that are not yours to worry about. It is enough to rest inside the scale of it. It is enough to feel how slowly and how certainly the pieces move. The two futures exist, both of them real in their possibility, and one of them is significantly warmer than the other, and the one that is warmer is the one that the scientists chose to study, because it is the one that carries the most consequential story for the life that currently lives on this planet, for the mammals, for the warm-blooded, internally heated, sweat-cooled descendants of the creatures that inherited the Earth after the last great extinction 66 million years ago. And that story, the full weight of what the numbers showed when the supercomputer was finally run forward, is what waits in the next movement of this long night. There is a paper. It has a title that is worth reading slowly, because the title does its work with a precision that most headlines never manage. Climate extremes likely to drive land mammal extinction during next supercontinent assembly. That is what it says. Not could threaten some species, and not may create challenging conditions. Extinction. The word sits there, plain and auditable, in a peer-reviewed journal called Nature Geoscience, published in September of 2023, and it names both the cause and the victim in the same breath: the supercontinent, the mammals, the extinction that follows when the first meets the second. The lead author is Alexander Farnsworth of the University of Bristol. He worked with co-authors including Benjamin Mills and Yong-Yun Hu, and together they built something that had not been built before in quite this way. A model that took the full machinery of climate science and pointed it not at last Tuesday's weather, not at the end of this century's warming, but at a world 250 million years from now. a world that no person will ever stand in, that no instrument will ever measure, that no satellite will ever photograph. And yet the model ran, and the model returned numbers, and the numbers were not comfortable. The machine they used was the HAD-CM3L. It runs at the Met Office in the United Kingdom, the institution that has been forecasting British weather since the 19th century and whose computational descendants now sit among the most capable climate engines on the planet. When you check whether to bring an umbrella tomorrow morning, somewhere behind the forecast is a lineage of modeling that descends from this same family of machines. The HAD-CM3L is a coupled climate model, which means it does not calculate the atmosphere alone. It links the atmosphere to the ocean to the land surface to the ice, and it lets them all speak to each other in the slow, iterative language of physics. Energy in, energy out, moisture moving, temperature shifting, pressure adjusting, season following season in the silicon-based arithmetic of a machine far too fast for human hands. What Farnsworth and his collaborators did was to load that machine with a different set of boundary conditions. Instead of today's continental arrangement, the scattered, ocean-buffered land masses we know, with their polar ice and their temperate zones and their enormous moderating seas, they gave the model a supercontinent. Specifically, they gave it Pangaea Ultima. They gave it the world that waits at the far end of the Atlantic's closing, the world that forms when the Americas have rotated back and the ocean between them and Eurasia has been consumed and the land has pressed itself together near the equator in a single massed gathering of rock and soil. And then they asked the model what the climate of that world would be, given everything else that would also be true at that moment in time. The model ran, and what came back, what the numbers showed when the long arithmetic was finished, was a picture of a world that most of the land surface of that future continent would be, month after month, between 40 degrees Celsius and 70 degrees Celsius, not at its most extreme, not in an unusual heat wave, routinely, monthly. The kind of temperature that, sustained, creates an environment in which the mammalian body has no recourse, no strategy, no path to survival, except to not be there. 40 degrees Celsius is the temperature at which a human being is considered to have a dangerously high fever. It is the kind of heat we associate with serious illness, with the body pushed to its outermost operating limit, with a condition requiring intervention, and that is 40 degrees. The model showed regions where monthly temperatures would sit not at 40, but at 50, at 60, approaching 70, temperatures that exist today only in the most extreme desert environments, in Death Valley at its annual peak, in the Lut Desert of Iran, which holds some of the highest land surface temperatures ever recorded. Temperatures that even the hardiest desert mammals endure only by retreating into burrows, by being nocturnal, by shaping their entire existence around the avoidance of the hours when the sun is high. In the world of Pangaea Ultima, there would be nowhere to retreat to. The burrow has a floor, the night still has an ambient temperature. The mountain range that today offers altitude and coolness is itself embedded in the interior of a continent that, from any direction, requires crossing thousands of kilometers of baking land before anything resembling ocean moderation is reached. There is no nearby sea to cool the breeze. There is no convenient coastline within a day's travel. There is only the land and the air above it and the sun that beats down on both. And here is where the three compounding forces come into view. Not one of them alone is enough to make a world unlivable for mammals. But the study's central finding, the thing that makes it genuinely new rather than a reworking of what was already known, is that these three forces do not operate separately. They operate together. They arrive at the same moment in geological time, each one amplifying the others, stacking their effects in a way that the model captures, and that intuition, reasoning from any single factor alone, would badly underestimate. A trap that closes from 3 directions at once is a different kind of trap than one that closes from one, and the difference matters enormously for anything trying to live inside it. The first force is the Sun itself. This is the one that operates on the longest timescale of the 3, the one that has been true for billions of years and will be true for billions more regardless of what the continents do or do not do. The Sun is not a stable, fixed object. It is a star in the process of fusing hydrogen into helium in its core, and as it does, its core slowly contracts and heats, and as the core heats, the fusion reactions produce more energy, and that energy works its way outward and eventually reaches the surface and leaves as light. The result is a sun that brightens, slowly but measurably, over geological time. The rate is approximately 1% per 110 million years. It does not sound like much. 1% over 100 million years is a change so slow that no civilization, no species, no ecosystem could ever detect it happening. But accumulated across the deep time between now and the formation of Pangaea Ultima, accumulated across 250 million years of that slow, relentless brightening. The increase reaches approximately 2.5%. 2.5% more energy from the Sun delivered to a planet every second of every day. 2.5% sounds modest, but the climate system is not linear, and a small increase in the total energy input can have effects disproportionate to the percentage when the system is already warm, when feedbacks are active, when water vapor in the atmosphere amplifies warming, when ice that might have reflected sunlight is absent. The Sun in the age of Pangaea Ultima is measurably, calculably, physically brighter than the Sun of today, and the model accounts for this. The additional energy is baked into every temperature it returns. The baseline is higher. Before the continents have done anything, before the volcanoes have spoken, the ground simply receives more. The second force comes from the ground itself, from the process of assembly, from the movement of the lithospheric plates as they converge. When plates collide, when continents press against each other, an oceanic crust descends into the mantle. At subduction zones, the rock that goes down is recycled in the heat of the deep earth. And as the planet's interior processes that rock, as the mantle digests what the subduction zones deliver, carbon dioxide is released. It rises through volcanic pathways. It enters the atmosphere through eruptions, through hydrothermal venting, through the vast complex of volcanic activity that tends to accompany periods of active plate convergence. The assembly of a supercontinent is, among other things, a geological era of elevated volcanic output. The atmosphere of Pangaea Ultima in the model carries a CO2 concentration that has been driven upward by this volcanic activity. Modeled atmospheric carbon dioxide potentially doubles towards 600 parts per million or higher, compared to pre-industrial baselines driven by the tectonics themselves, not by anything biological, not by any industry, but by the long exhalation of the planet's interior as it reorganizes its surface. And carbon dioxide in the atmosphere does what carbon dioxide does, which is to retain heat. It is a greenhouse gas. It absorbs infrared radiation that would otherwise escape to space, and it re-radiates that energy back downward, and the surface and the lower atmosphere warm in response. The physics is the same whether the CO2 comes from burning fossil fuels in the present century or from volcanic eruptions over millions of years in the deep future. The molecule does not care about its origin. This is an important distinction to hold clearly, and the study holds it clearly. The CO2 rise in the Pangaea Ultima model is tectonic and volcanic in origin. It is not connected to present-day human activity. The heat that the model projects is geological in its cause, solar in its amplification, and separated from anything happening today by a gulf of time so vast that the two events, present warming and the supercontinent heat, do not belong in the same sentence as causes of the same problem. They are different problems in different epochs, sharing only the physics of the greenhouse effect and nothing else. The world of Pangaea Ultima is not a consequence of this century. It is a consequence of plate tectonics, of stellar physics, and of 100 million years of slow convergence, and it will arrive in its own time regardless of anything that the current inhabitants of Earth do or do not do. The CO2 picture has another dimension worth holding because the story is genuinely double-edged and the study is honest about the tension within it. Over hundreds of millions of years, there is a process called silicate weathering that tends to pull CO2 downward. When rain falls on exposed silicate rock, granite, basalt, the kinds of rock that make up the continents, it reacts with the carbon dioxide dissolved in the water, and through a long chain of chemical steps that carbon is eventually deposited on the seafloor as carbonate sediment and locked away. It is the planet's slow thermostat, operating over millions of years, tending to counteract carbon dioxide rises by gradually drawing the gas out of the atmosphere. Over the very long run, across hundreds of millions of years, this process has a cooling effect. In the far future, further even than Pangaea Ultima, the silicate weathering thermostat is expected to draw CO2 so low that it begins to threaten C3 plant photosynthesis and then eventually C4 plant photosynthesis, in a different kind of planetary crisis driven by carbon starvation rather than carbon excess. But during the assembly of Pangaea Ultima, the model shows the volcanic spike winning. The rate of CO2 outgassing from the supercontinent's active tectonics outpaces the rate at which weathering can draw the gas down. The spike plus the brightened sun work together, and together they push the temperatures into ranges that the weathering thermostat cannot quickly correct. It is a matter of rates. The volcanic input is fast, in geological terms. The weathering drawdown is slow, and in the window of assembly fast beats slow, and the atmosphere accumulates what the interior is releasing faster than the rocks can capture it. So the second force stacks onto the first. A brighter sun is already delivering more baseline energy. Into that already warmer world, volcanic CO2 is being injected at rates that raise the greenhouse effect further. The model captures both. The temperatures are the product of both, and if that were all, it would already be alarming. But the third force is the one that turns a difficult climate into a lethal one for most of the interior of the continent, and it is the force that is perhaps the most unfamiliar, the least intuitive, and in some ways the most quietly devastating of the three. Continentality. It is a word that describes something simple once you understand it, and something vast in its consequences when taken to its logical extreme. At its heart, it is just this. The ocean moderates temperature, and the further you are from the ocean, the less of that moderation you receive. Water has a high heat capacity. It takes a great deal of energy to change the temperature of a large body of water, and it releases that energy slowly. The ocean absorbs heat in summer and releases it in winter, and the air that passes over it carries some of that moderation to the land nearby. Coastal cities are famously mild compared to inland cities at the same latitude. San Francisco, sitting at the edge of the Pacific, rarely sees the temperature extremes that Sacramento, a few hours inland, experiences regularly. London, surrounded by ocean on multiple sides, has winters mild enough to grow palms in sheltered spots, while Moscow, at similar latitude but deep in the Eurasian interior, endures temperatures that drop far below freezing for months. Central Asia today is one of the best illustrations of continentality at a scale large enough to feel significant. Ulaanbaatar in Mongolia is sometimes cited as the coldest national capital on Earth, experiencing winter temperatures that descend below -30 Celsius and summer temperatures that can climb above 35. The range is enormous, 60 or more degrees between the coldest winter days and the warmest summer ones, because there is simply no nearby ocean to buffer it. The air that arrives in winter is cold continental air from the north, with no warmth stored in any nearby sea to soften it. The air in summer heats over the vast interior with no cool maritime influence to moderate it. The continent makes its own extremes. Central Australia tells a similar story. The interior of the Australian continent is one of the driest, hottest places on Earth. Not because of its latitude alone, and not because of its geology alone, but because it is far from the ocean. The coasts of Australia are relatively temperate. The interior is not. The distance from the sea is measured in heat. Now imagine that the Atlantic has closed. Imagine that the Americas have rotated back into Eurasia and Africa, and that the land that was once distributed across 6 continents with ocean between all of them has been pressed into one. The interior of that continent, at the dead heart of Pangaea Ultima, the part of the land that is furthest from any coast in every direction, is not a few hours from the sea. It is not a few days. It is thousands of kilometers. In every direction the interior reaches, and no ocean moderates it. No maritime air masses cross into it with any meaningful moisture or thermal buffer remaining by the time they arrive. The continentality of Central Asia today, which is already extreme by any human standard, is modest compared to what the center of a fully assembled supercontinent would experience. Pangaea Ultima's interior would represent continentality at its theoretical maximum, the concept taken to its furthest possible expression on a planet the size of Earth. And Pangaea already showed us this was not speculative. The most recent supercontinent, the one whose breakup we are still living in the aftermath of, had a documented interior climate that the geological record has preserved for us. Pangaea's vast interior was characterized by what geologists call the mega-monsoon, a pattern of extreme seasonal rainfall on the continental margins combined with deep, savage aridity in the interior. The word mega-monsoon does not mean simply a large monsoon. It means a monsoon amplified to a scale that modern monsoons, constrained by the presence of ocean all around, cannot reach. In the interior of Pangaea, the seasons were brutal. The continental heart received little rain. The red beds and evaporates in the rock record from that era record a landscape of dramatic extremes. Searing heat, profound dryness, a climate shaped by the simple fact that the interior was too far from any ocean for moisture to reach it. That was Pangaea assembled in a world where the sun was slightly dimmer than today, where CO2 levels were different, where the geometry was different from what Pangaea Ultima will be, and even then the continental interior was a harsh, marginal place for life. Pangaea Ultima assembles under a brighter sun with higher CO2 in a geometry the model places closer to the equator, where solar input is at its most direct, where the angle of the sun's rays delivers maximum energy to the surface. The continentality effect is applied not to a high-latitude gathering, but to an equatorial one, where the absence of ocean moderation is coupled to the full force of tropical solar heating. Farnsworth and his collaborators loaded all 3 of these drivers into the HAD-CM3L simultaneously. They gave the model a brighter sun and let that baseline sink into every calculation. They gave it the elevated CO2 from volcanic outgassing and let the greenhouse effect propagate through the coupled atmosphere and ocean. And they gave it the supercontinent geometry, the single landmass, its vast interior sealed away from the ocean, the ring of coastlines as the only places where maritime air could still reach the land. And the model calculated the temperatures that resulted from all 3 operating at once. What it found was not the sum of 3 small problems, it was the product of 3 compounding ones. The brighter sun warms the baseline, the volcanic CO2 traps more of that energy and warms it further, and the continentality removes the only mechanism that might otherwise moderate the interior, the ocean, leaving the amplified heat with nowhere to go, no buffer to absorb it, no sea breeze to carry any of it away. Each driver, alone, might have produced a warm and challenging world. Together, they produced a world where monthly temperatures across most of the supercontinent sit between 40 and 70 degrees Celsius, where the heat is not a seasonal event but a persistent condition, where the question for any warm-blooded creature is not how to survive the summer, but whether survival is physically possible at all. And the answer for most of the interior and for most mammals is that it is not. This is the moment in the study where the biology enters, and where the numbers become not just geological facts, but physiological ones. Numbers that refer not to rocks and gases, but to the limits of bodies, to the precise physics of what happens when a living creature can no longer shed heat fast enough to survive. It is worth taking the time to understand the mechanism because it is precise, and because understanding it is what makes the study's conclusion feel earned rather than alarming. Mammals maintain a constant internal body temperature. This is endothermy. It is the hallmark trait of the class, the thing that makes a mammal in the deepest physiological sense. A human body runs at approximately 37 degrees Celsius, regardless of whether it is standing in snow or standing in sunshine. A dog, a whale, a bat, a mouse all maintain their own specific internal temperatures generated by metabolic heat, regulated by the body's thermostat. The mechanism is elegant and costly. It requires burning fuel constantly to generate heat, which is why mammals eat so much relative to their body mass compared to cold-blooded animals. It also requires mechanisms to shed heat when the environment is warm, because the metabolic processes that keep the body running always generate some excess heat, and if that heat cannot escape, the internal temperature climbs. And when it climbs too far, the proteins that run the body's chemistry begin to denature, and the body ceases to function. The primary heat-shedding mechanism available to most mammals in hot conditions is evaporative cooling. Sweating in humans or panting in dogs or other species-specific variants of the same fundamental strategy, using the evaporation of water from the body's surface or respiratory tract to carry heat away. The phase change from liquid water to water vapor requires energy, quite a lot of energy per gram of water, and that energy is drawn from the body's surface, cooling it. A human being sweating in heat is, in a very direct physical sense, running a cooling system that uses water as the working fluid and the evaporation into the surrounding air as the mechanism of heat removal. For this to work, the surrounding air must be able to accept more water vapor. If the air is already saturated with moisture, if the relative humidity is very high, evaporation is impeded. This is why a hot, humid day feels so much worse than a hot, dry day. In dry heat, sweat evaporates quickly and the cooling works. In humid heat, sweat sits on the skin, evaporation is sluggish, and the body retains more of its metabolic and absorbed heat. The effective limit of this system is described by the wet bulb temperature, a measure that accounts for both temperature and humidity together, representing the lowest temperature that can theoretically be achieved by evaporating water into a given parcel of air. A wet bulb temperature of 35 degrees Celsius is the critical threshold identified in a landmark paper by Stephen Sherwood and Matthew Huber, published in the Proceedings of the National Academy of Sciences in 2010. At a wet bulb temperature of 35 degrees, a human being at complete rest, in the shade, generating no excess heat, can no longer cool themselves by sweating. The air is too hot and too moist to accept the vapor that the body needs to shed. The body's internal temperature begins to rise. Within hours, this process, hypothermia, the uncontrolled elevation of core body temperature, becomes fatal. Not within days, within hours. A healthy adult, resting completely, unable to find any cooler air, would die. Not from dehydration, not from exertion, not from any avoidable circumstance. Simply from being in air that the body's cooling system cannot manage. Wet bulb temperatures of 35 degrees or above do not currently exist anywhere on Earth for sustained periods. There have been brief, rare spikes approaching this threshold in some of the world's most humid and hot regions, but sustained conditions at or above this limit are outside the range of the current climate. They are outside human experience. They are outside the experience of the entire history of our species. The Sherwood and Huber paper, published in 2010, was examining a potential future within the next centuries if warming continued under certain scenarios. It identified this threshold as a physiological absolute, not a matter of acclimatization, not a matter of technology, not something that evolution over short periods could address. It is a function of thermodynamics, it is a function of physics, and it applies to all mammals, not only humans, though the exact wet bulb limits vary somewhat with body size and species-specific physiology. In the world of Pangaea ultima, the model returned temperatures that in the interior and across much of the land surface would produce wet bulb temperatures well above this threshold. The heat and the humidity combine in the model in a way that makes the continental interior not merely uncomfortable and not merely dangerous, but physiologically lethal to any mammal with a body temperature in the range that mammals carry. The high humidity regions within the supercontinent are in some ways the most lethal because it is not the maximum temperature alone that kills. It is the combination of heat and moisture that defeats the evaporative cooling system, and those combinations can occur at temperatures lower than the absolute maximums the model shows. The study quantifies the result. Across most of Pangaea ultima, the land would not be habitable for mammals, and the numbers that remain, the fraction of the supercontinent's land surface where monthly temperatures stay within range that mammals could theoretically survive, is somewhere between 8% and 16%. The coastal fringes, the polar margins, the thin ring of land where the ocean is still close enough to send its moderating influence inward, where latitude or elevation or proximity to water offers some retreat from the baking interior. Between 8 and 16%, the rest is outside mammalian tolerance. The rest is too hot, too often, for too long. In a world where all the land is one, and most of that one land is lethal to warm-blooded creatures, that is not a crisis of habitat loss in the way we usually think of habitat loss. It is something more fundamental. It is the thermodynamic boundary of what a mammalian body can exist inside, drawn across most of a continent. And the bodies cannot change it by moving because there is almost nowhere to move to, and they cannot change it by acclimatizing because the wet bulb limit is not a limit of behavior or culture or physiology in the ordinary sense. It is a limit of physics. This is what the model returned. This is what Farnsworth and his co-authors published in September 2023 in Nature Geoscience, with the model named and the methods documented and the numbers in the tables for anyone to verify. A British supercomputer built to forecast tomorrow's weather turned 250 million years forward, and what it found at the end of that long calculation was a world that 3 compounding forces had conspired to make uninhabitable for the creatures that currently hold the planet's land surface. A sun slightly but measurably brighter, a volcanic atmosphere slightly but significantly richer in carbon dioxide, and a continent whose interior is sealed away from the ocean with a finality that no other planetary configuration can match. Each force alone might have been managed. Each driver operating without the others might have produced a difficult climate that life found ways to negotiate. Evolution is patient. Life has survived enormous changes over the billions of years this planet has been inhabited. But the 3 forces do not arrive separately. They arrive together at the same moment in the planet's tectonic history, stacked one on top of the other, compounding in a way that the model captures, and that no single-factor analysis would predict. The brighter sun raises the baseline. The volcanic CO2 traps more of the additional energy. The continental interior removes the buffer that might otherwise moderate both. The heat accumulates in the rock and the air. The seasons become violent. The daily swings become extreme. The wet bulb temperature climbs past the threshold that mammalian physiology can navigate, and the interior of the continent becomes, month after month, not a marginal place, not a stressful place, but a place where warm-blooded creatures with internal temperatures in the high 30s cannot exist. The story of how three forces conspired to close the trap is now, in its mechanism, complete. And it waits there in the geological future like a slow, patient fact, not a catastrophe in the human sense, not a sudden event, not a disaster that arrives on a Tuesday. It is an accumulation, a long, gradual closing of conditions around a particular kind of biology. A process so slow that no individual creature will perceive it happening, and so certain that the model, given the inputs, can return no other answer. And yet the question of what remains, of what might survive in the thin, habitable rind at the edges of that world, and what might inherit the hot interior that mammals have vacated, that question is still open. The story does not end with the three forces stacking. It continues into the edges of the continent, where the ocean still reaches, and into the biology of what kinds of creatures can live where mammals cannot. And it continues into the two separate timescales, the supercontinent heat at 250 million years, and the sun's longer terminal accounting further out, and into the quiet, wistful question of whether anything recognizable as our descendants would be present to witness any of it at all. But those movements are ahead, and there is no need to hurry into them. The mechanism is here, laid out in the arithmetic of the model, in the physics of wet bulb temperature, in the compounding of three planetary forces on a continental geometry, that the Atlantic's closing is already, in its first centimeters, beginning to assemble. The trap is real and its mechanism is specific, and the specificity is what makes it rest differently than a vague prediction. It is not a warning. It is not an alarm. At 250 million years, it is something closer to a natural fact about the planet we live on, a deep time truth that the supercomputer surfaced, and the scientists named, and the journal published, and the mathematics confirmed. The sun is brightening. The volcanoes will speak when the plates converge. The ocean will retreat from the interior when the land is pressed together. And the model, running the three of them together, returned temperatures between 40 and 70 degrees Celsius across most of the land, and found only 8 to 16% of that surface where any mammal might still exist. Those are the numbers, clear, named, auditable, published in September of 2023 in Nature Geoscience under the names of Alexander Farnsworth, Benjamin Mills and Yongyun Hu, using the HAD-CM3L supercomputer of the Met Office, the same long lineage of machines that tells you whether to carry an umbrella turned 250 million years forward into the long, inevitable, quiet future of this world. And so we arrive at the finding itself, not at a theory, not at a simulation artifact or a researcher's speculation, at a finding, the word scientists use when the model has run, the parameters have been checked, the peer review has done its slow and careful work, and what remains on the page is something that can be stated plainly without hedging the substance, even while hedging the details. The finding is this. Across most of what will one day be Pangaea Ultima, the monthly temperature will routinely sit between 40 degrees and 70 degrees Celsius, 104 degrees to 158 degrees Fahrenheit if you need the other scale, not peak temperatures on the hottest afternoon of the hottest summer. Monthly averages, the kind of heat that is simply the ambient condition of the world, the background noise of the air, the temperature of the shade, the warmth of a cave or a burrow, or whatever shelter a creature might crawl into looking for relief. 40 to 70 degrees Celsius, month after month across most of the land, and only 8 to 16% of that land surface would remain where any mammal could survive. Let that fraction sit for a moment. 8 to 16%. Take the total land area of the supercontinent and shade almost all of it dark. Shade it the color of uninhabitable heat, and what you are left with, the pale, thin remainder, is the rind, the edge. The narrow, surviving margin where ocean is still near enough, or latitude is still high enough, to hold the temperatures somewhere a mammal's body can still function. 8 to 16%. Not a mass extinction in the classical sense, where an asteroid darkens the sky and the cold comes fast and everything adjusts or dies within a geological eye blink. Something slower, and in its slowness, something more total. The heat is not a catastrophe that arrives, it is a condition that assembles degree by degree over millions of years until the land that was livable is simply no longer livable, and the places where life retreats grow smaller and smaller and smaller still. But to understand why those numbers are what they are, why 40 to 70 degrees, why 8 to 16%, and not 50%, not 30, you have to go into the physiology. You have to go into what it actually means in the engineering of a body to be warm-blooded on a planet that is growing warmer. Because the thing the numbers describe is not simply heat, it is a failure, a specific mechanical failure of a specific, elegant system. And that system is the one that made mammals what they are. Think about what warm-bloodedness actually does. The technical word is endothermy, and it means that your body generates its own heat from the inside, or from metabolism, from the burning of fuel in every cell, and holds itself at a fixed, high, internal temperature regardless of what the world outside is doing. When it is cold outside, you burn more fuel to hold your temperature. When it is warm outside, you shed heat into the environment so your internal temperature stays the same. The whole system depends on a simple physical fact. Your body is warmer than the air around it, and heat flows from warm to cool, so the heat your metabolism generates can always flow outward into a cooler world. You are, in thermal terms, a furnace surrounded by a larger, cooler room. The heat always has somewhere to go. This is the gift. This is what mammals and birds developed, what made them so spectacularly adaptable across the Cretaceous, and then so spectacularly dominant when the asteroid came and the dust settled, and the cold-blooded dinosaurs, unable to generate their own heat, could not hold themselves together in the sudden global winter. The warm-blooded survivors, the small, burrowing, metabolically flexible proto-mammals, persisted, and in the 66 million years since, their descendants have spread across every climate and every latitude on the planet, from the Antarctic seals to the Arctic foxes to the camels in the Sahara and the yaks on the high Tibetan plateau, all of them running their internal furnaces, all of them holding their body temperatures in that narrow band that keeps their enzymes working and their neurons firing and their muscles contracting. The range is not wide. Most mammals operate with a core temperature somewhere between 36 and 39 degrees Celsius. Some a little higher, none very far outside that band without serious trouble. Now take that furnace and put it in a room that is no longer cooler than it is. Put it in a room where the air temperature is climbing past 35 degrees, past 38, past 40. The heat that the body generates has nowhere to go. The gradient reverses. Heat flows from warm to cool, but now the air is as warm as the body, or warmer, and the outflow stops and the body's own metabolic heat begins to accumulate. The internal temperature climbs. The enzymes that depend on a narrow temperature range begin to falter. The proteins begin to destabilize. The brain, the most thermally sensitive organ, begins to fail first. This is heat stroke in its most fundamental physical description. And for most mammals, sustained exposure to ambient conditions above roughly 40 degrees Celsius for any extended period leads there directly. The body's answer, the evolved emergency system, is sweating. You push water to the skin's surface, and when that water evaporates, it carries heat away with it. The same physics that makes you feel cool stepping out of a lake on a breezy day, the same physics that makes a clay pot of water cooler than the water inside when it sits in a dry wind. Evaporation steals heat. A sweating body in dry heat can manage temperatures well above what it could survive in still, dry shade. This is why a healthy human being drinking enough water can function in 40-degree desert heat. The evaporative cooling is working, the heat is leaving the surface faster than the metabolism and the environment are adding it. But evaporation has a limit, and that limit is the wet bulb temperature. The wet bulb temperature is not the temperature you read off a standard thermometer. It is the temperature you get when you wrap a thermometer's bulb in a wet cloth and let evaporation cool it as much as it possibly can in the current air. What you are measuring is the temperature that evaporative cooling can reach, the lowest temperature a sweating surface can achieve in that particular air. When the air is dry, evaporation is efficient, and the wet bulb temperature is much lower than the dry bulb temperature. When the air is saturated with humidity, evaporation slows because the air is already full of water vapor and can absorb little more, and the wet bulb temperature climbs toward the dry bulb temperature. At 100% humidity, they are the same. The critical threshold, the one identified in the physiological literature and formalized by Sherwood and Huber in a 2010 paper in the Proceedings of the National Academy of Sciences, is a wet bulb temperature of 35 degrees Celsius. At a wet bulb temperature of 35 degrees, a human body at rest, not exercising, not generating extra metabolic heat, simply existing, can no longer cool itself by sweating. The air is too warm and too wet to take the heat away. Whatever heat the resting metabolism generates simply stays. The core temperature begins to rise, and within a matter of hours, the result is fatal. 35 degrees wet bulb, not 35 degrees dry. You could have a dry bulb temperature of 55 or 60 degrees and a wet bulb of 35, and it would be right at the edge. You could have a dry bulb of 45 degrees and high humidity and be well past the line. The wet bulb temperature is the more honest measure of what heat does to a body because it accounts for the air's capacity to absorb the body's only real cooling mechanism. And in the interior of Pangaea Ultima, in the model's projection, both dry bulb and wet bulb temperatures in many regions would pass that line. The air would be too warm and too wet from the immense monsoon systems that gather and fail to deliver across a closed-off interior to allow the bodies of mammals to function, not in summer, not in the afternoon peak. In the monthly average, the condition would be ambient. This is the specific shape of the failure, not fire, not flood, not impact. A thermal threshold crossed, a threshold written into the physics of evaporation and the biology of warm-bloodedness, crossed slowly across millions of years until the crossing becomes complete across most of the available land. The furnace finds itself in a room that will not accept its heat. And the room is getting warmer from 3 directions at once. The sun is delivering more energy. The volcanoes are adding insulation to the atmosphere. And the ocean, the great moderator, the thermal buffer that holds coastal temperatures in their narrower range, is simply not there for the interior. 3 forces, none of them catastrophic alone, none of them new to the planet's experience, converging on a geography that makes all 3 of them worse at the same time. And mammals, endotherms, warm-blooded, high-temperature dependent, happen to be the clade that has inherited the planet at the moment this geometry begins to close. 66 million years ago, warm-bloodedness was the advantage that survived the cold. 250 million years from now, in the model's projection, warm-bloodedness would be the liability that could not survive the heat. It is, if you sit with it long enough, one of the more quietly astonishing ironies in all of natural history. The very adaptation that opened the world to mammals could narrow it to almost nothing. The gift and the trap are the same mechanism, seen from different ends of the thermometer. So the question becomes, where do the survivors go? The 8 to 16%. The pale rind on the shaded map. Where is it, and what does it look like, and what kind of life would it hold? The honest answer is that the model gives us a direction rather than a precise geography, because the details of coastlines and elevations and ocean circulation patterns on a continent that does not exist yet are genuinely beyond what any model can claim to specify. But the direction is clear. The habitable margins would persist where two conditions are met: proximity to an ocean and sufficient latitude. The coast, where the sea can still moderate the temperature, blunting the daily and seasonal extremes that the interior experiences without restraint. And the poles, or the areas closest to them, where the geometry of the Earth itself delivers less of the brightening sun's energy per unit of surface, and where, if Pangaea Ultima sits as the model positions it, near the equator and the tropics, the polar and subpolar fringes would be the coolest remaining land. Think of the supercontinent's edge as a narrow shoreline ecology, a thin strip where something like survivable temperature persists, and then the interior stretching away behind it, thousands of kilometers of heat-scoured land, the dead heart of the world. Life would not live there, not mammalian life. The interior would be a kind of permanent, uninhabitable zone, a thermodynamic desert, not of water shortage, but of heat saturation, where any warm-blooded body that wandered in from the edge would begin its irreversible failure within hours. The coastal strips would themselves not be easy. The model does not project them as cool or comfortable. They would be the least intolerable part of a planet that had, across its main body, become intolerable to mammals. Narrow refugia. The word researchers use for the places where life retreats when climate changes faster than evolution can follow. The refugia that the Ice Age species used pulled back into their last remaining pockets of habitat, waiting for conditions to shift again. On Pangaea Ultima, the shift back would not come. The sun would not dim. The CO2 from the volcanism would not quickly clear. The ocean would not return to the interior. The refugia would be the whole of what remained, and they would be contracting, not merely pausing. And into those narrowing margins, evolution would be doing what it always does, finding whatever works, discarding whatever does not, and paying no attention at all to our preferences about which creatures should inherit the outcome. Some things would do better than mammals. It is an inference, and it should be held as one. The model projects temperature, species composition, and what survives on a hot planet in 250 million years is not something any model specifies with confidence. But the physical reasoning is straightforward. Reptiles are ectotherms, cold-blooded in the common parlance, though the term is misleading because they are not cold, they are simply not internally heated. Their body temperature tracks the environment's temperature, and this means they do not generate metabolic heat that must be shed into the surrounding air. At high ambient temperatures, a reptile is not fighting its own metabolism. It simply is the temperature of the world around it. This does not make extreme heat comfortable for reptiles. Proteins denature, enzymes fail in reptiles too, and there are upper thermal limits beyond which no ectotherm functions. But those limits are generally higher than the wet bulb constraint on endotherms, and in a world where ambient temperature is the primary challenge, the endotherm's internal heat generation becomes a burden the ectotherm does not carry. Insects, similarly, are extraordinarily heat-tolerant compared to most mammals. The biochemistry of insect life can function at temperatures that would be lethal to warm-blooded animals within hours. Plants too, particularly the heat-tolerant lineages, the species adapted to tropical and arid conditions, and would likely find corridors of survival that mammals could not occupy. The planet would not be empty, it might not even be quiet. But the age of mammals, the 66 million-year tenure that began in the cold and dark after the asteroid that gave us everything from shrews to whales to the bipedal, large-brained lineage that eventually wrote down what we know and wondered about what would come, might find its ending not in fire from the sky, but in the slow, measured, geological inevitability of a planet rearranging itself the way it always has, in cycles older than complex life itself. There are two deadlines in this story, and it is worth being clear about both of them because they are separate, and conflating them produces a confusion that the mathematics does not deserve. The first is the supercontinent deadline. Roughly 250 million years from now, if the Atlantic closes and Pangaea Ultima assembles near the equator, the model projects the conditions we have been describing. The three stacked forces, the temperatures between 40 and 70 degrees, the 8 to 16% of habitable land, the wet bulb threshold crossed across most of the interior. This is the tectonic and solar deadline. It is real, it is modeled, it is auditable in the September 2023 paper in Nature Geoscience, and it is the product of plate tectonics and a brightening star, not of anything that happens in a human lifetime, not of anything that a generation of people living today could cause or prevent. It is a geological clock running on deep time, and the distance between now and its culmination is longer than the entire span of complex animal life on Earth. The second deadline is further out and more absolute. In approximately 1 billion years, the Sun will have brightened enough, following the same steady luminosity increase that underlies the 2.5% figure in the 2023 study, but carrying that trend 3 to 4 times further to trigger what is called a runaway moist greenhouse. The term describes a specific atmospheric transition. Water vapor, driven into the upper atmosphere by intense surface heating, begins to be broken apart by ultraviolet radiation. The hydrogen escapes to space, and the oceans gradually lose their water to the sky. Once that process begins, it does not reverse. The oceans would disappear. The surface would become uninhabitable, not merely for mammals, but for all complex life, and eventually for life of any kind. Earth would enter a phase not unlike Venus in its broad outlines, a hot, dry, pressurized world from which the water that allowed everything here to exist would simply be gone. That is the final deadline, 1 billion years, and it comes after the supercontinent heat event, not simultaneously with it. The tectonic heat at 250 million years is not a preview of the moist greenhouse. It is a separate trap on a different mechanism on the way toward that later terminal horizon. The Sun is brightening continuously, and that brightening runs through both events. It contributes the 5% extra energy to Pangaea Ultima's heat, and it delivers the far larger increase that eventually triggers the atmospheric escape. But they are distinct thresholds separated by 750 million years, and the first one is about geography and continental geometry in a way that the second is not. It is also worth saying clearly what the supercontinent event is not. It is not today's climate change. The mechanism is entirely different. Today's warming, the increase in global average temperatures driven by the accumulation of greenhouse gases from human industrial activity over the past 2 centuries, is anthropogenic. It operates on a time scale of decades to centuries, and it is already measurable and already consequential. The tectonic heat of Pangaea Ultima is driven by plate motion and solar physics, operates on a time scale of hundreds of millions of years, and is not influenced in any meaningful way by what human civilization does or does not do in the next 100 years. The CO2 in the 2023 model's lethal projection comes from supervolcanism unleashed by the convergence of continents, from the same tectonic engine that built the Himalayas and the Andes, operating over geological time, not from combustion engines and power plants. Keeping those mechanisms separate is not a political position, it is an accurate description of the physics. A person can be deeply concerned about the near-term changes happening now and also find the deep time story of Pangaea Ultima one of the most extraordinary and consoling things geology has to offer, without confusing the two or implying that one diminishes the other. They are different stories at different scales, connected only by the broad fact that carbon in the atmosphere warms the planet, which is a physical truth that applies across all timescales while playing out very differently depending on what is adding the carbon and over what period. There is one more thread to pick up, and it is the most speculative and also the most quietly human, and so it deserves to be held carefully. The researchers who published the study and the press coverage that followed occasionally frame the question in terms of our distant descendants, whether any lineage tracing back to Homo sapiens might still exist in some form 250 million years from now, and whether that lineage might be among the mammals struggling in the narrowing refugia. It is a frame that has an obvious emotional pull. It makes the geological scale personal in a way that plate tectonics alone does not. But 250 million years is a span that asks us to hold two things at once and let them coexist without resolution. The first is that mammalian life has existed for roughly the same length of time. Perhaps 250 million years back takes us to the early Triassic, to the therapsids, the mammal-like reptiles from which our lineage eventually emerged, creatures so different from a mouse or a bear or a human being that the word ancestor, while technically accurate, barely does the distance justice. The second is that in all of that time, across all of those lineages, no single species has persisted unchanged. Species change. Lineages branch and go extinct. What survives is not the individual form, but the thread of inheritance, the genetic continuity that passes through body plans that become unrecognizable across tens of millions of years. Something that could legitimately be called the descendants of today's mammals will almost certainly exist 250 million years from now, if mammals survive that long at all. But whether any of those descendants would be recognizably related to us, whether they would carry anything we would call humanity in any biological or cognitive sense, whether they would look at the world in a way that would be meaningful to us, all of that is not a question science can answer. It is a question that simply opens and stays open, and perhaps that is the right way to hold it, as a loop that need not close, as a wondering, not a prediction. There is something strangely peaceful in that if you let yourself feel it rather than pushing past it. The question of whether something descended from us will be there, on the edges of Pangaea Ultima, in the narrow strips where the ocean still breathes and the heat is merely terrible rather than absolute, trying whatever biology has given them to work with. That question is not answered by the model. The model projects temperature. It does not project who will be standing in it. And 250 million years is so far from now, so far beyond the horizon of any concern that a person lying in a quiet room tonight could reasonably carry, that the not knowing becomes a kind of gift, a piece of the future that is simply outside the reach of anxiety. Whatever is there will not have known you. It will not have needed you to worry on its behalf. It will be whatever the planet and the deep time and the billion small evolutionary decisions between now and then have made it, and it will carry, in the structure of its cells, in the physics of its metabolism, the long inheritance of every living thing that came before it, including, somewhere in that chain, something that was here tonight, something that breathed and was warm. The planet's story does not end with the heat of Pangaea Ultima. Even if mammals are reduced to their narrow coastal margins, Even if the changing of the guard comes, and the ectotherms and the insects and whatever new life the deep time invents take the interior that warm blood can no longer hold, even then the story continues. The supercontinent will not stay assembled forever. The Wilson cycle does not stop at assembly. It breathes in and then it breathes out. Pangaea Ultima will eventually rift apart the same way Pangaea did, the same way Rodinia did before it, the same way Columbia and Pannotia and all the older assemblies did, cycling back and back through the deep history of a living planet. The interior will open again, the oceans will return to the spaces between the separating pieces, the temperatures in what were formerly dead heartlands will moderate as the water comes back, and life, whatever life has become by then, will spread back into the opened space and do what life always does when space opens. It will fill it. The planet is not a fixed thing, it is not a backdrop. It is a process, an old, slow, continuous process of assembly and rifting and heating and cooling and biological experiment and extinction and reinvention, running on a timescale so far outside human experience that even our deepest historical imagination barely reaches the edge of it. We know it happened because the rocks remember it. The stratigraphy, the paleomagnetism, the isotope ratios, the fossils, they are the record of previous assemblies and previous rifts, previous extinctions and previous radiations, previous versions of this same planet doing what this planet does. What the 2023 study did was take that record, extend it forward using the physics that produced it, and name what the forward extension looks like. And what it looks like for the window around 250 million years from now is a world that is genuinely too hot for most mammals. 3 stacked forces on a geometry that amplifies all 3 of them. A brighter sun, measurably and inevitably, because stars brighten as they age and there is no thermodynamic way around it. Volcanic carbon in the atmosphere, added by the same tectonic collision that makes the supercontinent, the same process that built the Himalayas and will build whatever mountains Pangaea Ultima grows along its suture lines. And the absence of ocean in the interior, the continentality made absolute, the dead heart of the world where no sea breeze reaches and no coastal moderation blunts the daily swing from brutal night to more brutal day. Against those 3 forces, acting in concert across the slow centuries of assembly, warm-bloodedness, endothermy, the adaptation that carried mammals across the end Cretaceous extinction, that filled the world with whales and bats and elephants, and the curious language-using primate that eventually published papers about this in peer-reviewed journals, would find its physical limits reached. The wet bulb temperature of 35 degrees, the line that Sherwood and Huber named and quantified, and that the physiology confirms is real, would be crossed across most of the available land, and crossed not seasonally but permanently, and the thin remaining margins would hold what they could hold, and no more. This is not a horror story. It does not feel like one at this distance. At 250 million years, the emotional register changes. The fear that attaches to near-term endings does not reach this far. What reaches this far is something older and quieter, something closer to awe at the sheer duration of the process, at the patience of a planet that assembles and disassembles itself over timescales that make all of recorded human civilization a single, thin line in the stratigraphy. The mammals that might find the interior of Pangaea Ultima uninhabitable are not people in any sense we would recognize. The world they would be retreating from is not the world we know. The sun that would be shining 2.5% brighter than it shines tonight would still be the same star, still the same engine of light and warmth that has made this planet livable for 4 billion years, simply further along its own slow, inevitable brightening. and the Earth beneath it all would still be doing what it has always done, moving, grinding, cycling, breathing continents in and out across the face of a planet that is itself moving through a galaxy around a star, in a process too large and too slow and too indifferent to anything as small as a species or a question to be described as either friendly or hostile. It simply continues. It has always simply continued. The Atlantic is widening tonight. Somewhere in the floor of that ocean, new crust is forming along a ridge that runs the length of it, pushing the Americas and Europe and Africa a centimetre or two further apart, the way they will be pushed every year, every decade, every million years, until the geometry of that widening meets whatever limit the planet places on it. The Pacific is contracting a little around its ring of subduction zones. The plates are where they are, and they are moving at the speed they are moving, and in 100 million years they will be somewhere different, and in 250 million years they will be somewhere different again. And what the 2023 study named is what the physics projects will be true of that future somewhere. That is what a supercomputer running a climate model forward 250 million years actually is. Not prophecy. Not alarm. Physics applied to geometry, applied to the known behavior of stars and atmospheres, and the known thermal physiology of the organisms that happen to be currently dominant. A careful statement about what the equations imply, hedged appropriately, published for review, available to be checked and refined and disagreed with and improved. The 8 to 16% is a number from a model, not a certainty. The 40 to 70 degrees is a range, not a precise reading. The outcomes for specific lineages, which ones are there? Whether any thread of our inheritance runs through to the narrow coastal strips of the supercontinent, are genuinely outside what the model claims. What the model claims is the temperature. And the temperature is what it is. Somewhere beneath you tonight, the rock is warm from the planet's interior heat, from the slow decay of radioactive elements laid down in the formation of the solar system 4.5 billion years ago, from the primordial heat of accretion that the planet has been releasing ever since. That warmth drives the plates. It has always driven the plates. It will drive them for billions of years yet, slowing gradually as the planet cools, doing its slow, patient, indifferent work across the deep time, assembling and rifting and assembling again, producing supercontinents and ocean basins and the temperature conditions that life in whatever form must work with. Tonight, it is working in your favor. Tonight, the continents are arranged and the ocean is distributed, and the sun is at the brightness, and the CO2 is at the concentration that allows a warm-blooded animal to lie still in a quiet room and breathe slowly, and let the heat of its own metabolism disperse comfortably into the air around it, the way mammals have been doing, in one form or another, for over 60 million years of unbroken inheritance. Tonight, the wet bulb temperature is nowhere near 35 degrees. Tonight, the world outside is, in thermal terms, exactly what endothermy needs it to be. The plates are moving, the sun is brightening, the Atlantic is widening at the speed of a growing fingernail, and somewhere on the far side of a span of time that has no human scale at all, the geometry will change and the forces will compound, and the model's finding will come to be true of some version of this world. But that is then. And this is now. And now is the vast majority of what the planet's hospitable life offers to the creatures who happen to be here for it. Let the distance of it settle around you. 250 million years, the whole tenure of warm-blooded mammals on this earth, from the therapsids forward, laid end to end and then laid end to end again 4 times over. A span so large it has no emotional content in the ordinary sense, only the quiet, almost restful recognition that you are standing at a particular moment in an extremely long process, that what is warm in you tonight is the inheritance of everything that came before and the ancestor of everything that will come after, and that the process will continue whether or not any particular form of it is present to observe. The supercontinent will form, the heat will come, life will find the edges and hold on, and then the edges will widen again when the rifting comes, and new life will fill the opened space. The planet breathes in millions of years, and we are the thought it is thinking right now, briefly, warmly, in the middle of an exhale. Let the wisdom settle soft. The rest will come on its own.